In this video, we're going to use a context to interpret function notation and derivative notation. And the context is that R of t represents the amount of rainfall that has accumulated, measured in inches, t minutes after 3 a.m. So if we're going to interpret the statement R of 120 equals 2.4, well, the 120 is an input, which was time in minutes after 3 a.m. So 120 minutes after 3 a.m. is 2 hours after 3 a.m. So at 5 a.m. and then what is it that's being measured is the amount of rainfall. According to this statement, the amount of rainfall is 2.4 and the units on that is inches. So that would be our first answer. Let's go on to the next one. R prime of 150 equals 0.1. Now we have a derivative. It's talking about how the amount of rainfall is changing. First off, let's go with where this is occurring at. So t equals 150 is 150 minutes after 3 a.m., which would be 5:30 a.m. So at 5:30 a.m., this is an instantaneous rate of change, so the amount of rainfall is increasing, and we know it's increasing because our derivative is positive. Now, what is it increasing by? 0.1, or is increasing by 1/10 of an inch. Now it's a rate of change, so it's something changing with respect to something else. Since our inputs are minutes, it's increasing by 1/10 of an inch per minute. Not every minute, it's happening just at 5:30 a.m. It's not talking about 6 a.m. We don't know that it's a linear rate, but at 5:30 a.m., the amount of rainfall is increasing by 1/10 of an inch per minute. Going on to our last statement. Interpret the statement R prime of 150 is greater than 0, R double prime of 150 is less than 0 in the context of the problem. So again, this is happening at 5:30 a.m. So at 5:30 a.m., the amount of rainfall, now since our first derivative is positive, we can say the amount of rainfall is increasing. Now since our second derivative at that point is negative, we know that it's increasing at a decreasing rate. And that is what we can say about the derivative notation in part C.